this is a fortuitous time to be having the PEER workshop. We are at a really important crossroads in our effort to develop a simulated ground motion database that is focused on earthquake engineering applications. And I'm happy to report, as a result of our workshop yesterday and getting feedback from 15 beta users, we are about to go live with the simulated ground motion database. And there'll be more information shortly from PEER about how you can sign up to get open access to this database. This is really a culmination of an effort that started in 2017, if you can think back that far, with the development of a lot of the computational tools by the DOE Office of Science that I'm going to summarize here in just a moment. And so we've gone through a period of research, computationally based research, to develop a high-performance tool that we can utilize to develop these databases. If you think about a simulated ground motion database, you have to have the computational infrastructure and framework to actually generate the simulated ground motions. As we strive to push to higher frequencies of engineering relevance and more dense motions, the computational aspects and having those aspects in hand are critically important to developing that database. Once we've gone through the discussion of the simulation capability that we're employing, I'm going to pivot very rapidly and do a quick summary of the database, what's going to be in that database, the characteristics of that database, and also how you access it. I'd like to acknowledge the really great team we've had working on this since 2017. We have two national laboratories, Lawrence Berkeley National Laboratory and Lawrence Livermore National Laboratory. Both of those laboratories are sort of at the bleeding edge of high-performance computing. And we're leveraging capabilities and people from both of those laboratories. We have connected with PEER on this because we wanted to ensure that what we get to in terms of the simulation ground motion database is of most relevance to the engineering community at the end of the day. And so in all of our workshops, and yesterday was no exception, we always have a poll and we take feedback from both practitioners and researchers in earthquake engineering to really help us craft what that simulated ground motion database is ultimately going to look like. So let me start with the computational capabilities that we've developed since 2017 at the national laboratories. And this was sort of a fortuitous development. In 2017, the DOE, U.S. Department of Energy, driven primarily by the Office of Science, made the decision that we needed to push ahead in high-performance computing leadership in the United States. This is typical. We sort of go through cycles on the high-performance computers of different architectures. And really the challenge that DOE laid down for itself was to develop the world's first exaflop computer. And exaflop, that's a term that not everybody's familiar with. It's a billion. And so an exaflop computer is a computer that can compute a billion floating point operations per second. And if you like, just the number I've shown down there is showing you that's 1 times 10 to the 18th floating point operations per second. So this was a big challenge. And the fundamental change in architecture to move towards these machines was moving away from CPU-based chips to GPU-based chips. And so you can just simply think of that as a CPU chip. In the older computers, did all the calculations sequentially in order. The new GPU systems can divvy up the work on the chip and do calculations in parallel. So that's a major departure, and it really mandated a very different construct for our software to make those computers effective and work well. So the DOE had a competitive call for proposals to develop a number of applications that would be ready and to get ready to work on these. The EQSIM framework that I'm going to talk about over the next couple of minutes was one of those that was actually accepted for proposal. And our proposal was actually to model all the way from the earthquake fault rupture, the propagation of those waves through the heterogeneous earth, then the interaction of those waves with infrastructure. So it was quite an ambitious proposal, and it spanned the disciplines in a multidisciplinary sense, from seismology to engineering, both geotechnical engineering as well as structural engineering. So that was the proposal. We were luckily funded, so we had a tremendous funded effort from 2017 to 2023 to help develop that workflow and get proficient on these computers. And that really has formed the basis of our simulated ground motion database, as you'll see in a few minutes. So what do we do? I'm going to briefly mention the major improvements. We started with the SW4 fourth order in time and space wave propagation code that was originally developed by Peterson et al. At Lawrence Livermore National Laboratory. And we did a whole slew of advancements to that in terms of getting it ready, both algorithms, new algorithms, and transitioning the architecture of that code from a CPU-based code to a GPU-based code. And on the right-hand side, I've just listed a few of the important things we did. One that was really, really important was SW4 up to that point in time was based on a regular grid. And so we went through and did a complete remapping of the gridding in that code with a curvilinear grid near the surface to handle topography, a Cartesian grid at depth to be efficient. And so we developed a graded approach, and that really allowed us to reduce the size of the models as we went to these very, very large sizes. We completely redid the I/O. And those of you that were at the workshop yesterday, you could understand from Hu-Jun Tang's presentation how much effort that was to really, these are really, really giant data sets, and you have to develop efficient ways of handling that data, often through compression to downsize that data, lossy compression. And so we did a lot of that. And then we did the readiness for the GPU-based platforms. We had to go into a lot of the inner loops in that code and actually modify those to do this parallel optimization on GPU chips. So it was a major effort. Important to the engineering community is, I think, is that we developed a very robust implementation of the domain reduction method. So we could really allow the geophysics code and the local engineering codes to communicate in a very rigorous way. Domain reduction method developed by BLAC allows you to honor and represent the complexity of the inclined waves that are coming into your site. Both in terms of inclined body waves and surface waves. That was a really, really important development. And we had to, you know, as you'll see, we're computing models in the geophysics models that are 200 or 300 billion grid points. So we had to do this very efficiently and develop workflows so that that connection could be carried out quite efficiently. So at the end of the day, we developed an end-to-end workflow that I don't have time to describe here, going all the way from the geophysics simulation, transferring those large data sets in two different flavors to the engineering community so they could either do a simple fixed base analysis with the ground motions at that site or do a fully coupled and potentially nonlinear soil analysis for their facility and get a distribution of risk. We really, a fundamental overarching objective was to get a very much clearer distribution of regional scale risk in this. So front of mind were three things in this development, and these were mandated by DOE. We had performance metrics. Number one, resolution. We wanted to increase the frequency resolution to frequencies relevant to engineering interests as part of this. Some of you may know that in these large-scale models, the computational effort varies as the frequency to the fourth power, so that's a very steep hill to climb. And so we really had to be right at our cutting edge to really increase that frequency resolution. Speed. I think in our first workshop, Norm Abrahamson had mentioned, you know, that's great. You can do one or two simulations, but that doesn't help us. We need you to be able to do a bunch of simulations to account for the uncertainties and the distributions in the parameters. So speed was quite important to be able to speed up these calculations so we could do many realizations, not one or two. Usability. This was not imposed by DOE, but this was imposed by us. We're dealing with data sets that are billions and billions of grid points in size, and you'll see some of those. We built in the notion of usability for the users into our development so that it would be easy to transfer this data and easy to manipulate these very large runs. At the bottom, I'm saying if we can achieve all three of these things, we can get to a state where these regional simulations are no longer heroic, they are routine, and that was a really important objective, and I think by and large we've gotten there. Let me just show you some of the results so you get a sense. I'm showing you the frequency increases that we attained. The model you see in the left was a model of the San Francisco Bay Area that we developed early in the ECP project. DOE judged all of our performance relative to that particular model, so that was our test case, 120 kilometers by 80 kilometers by 30 kilometers in depth. What I'm showing you on the top is the achievements in increased resolution throughout the life of the project. When we first started the project in 2017 on the Cori CPU supercomputer at Berkeley Lab, we could compute this to a little bit less than 4 hertz, about 3.5 hertz. As a result of the algorithm developments, the design of the workflow and I/O and the transition to GPU platforms, we successively increased that performance until we got to into the project 15 hertz. We could compute the Bay Area at 15 hertz. Do we want to do that right now? Maybe not, because our geologic data is a little lacking, but we wanted to remove simulation as a barrier to moving forward with these high performance simulations. So this was a very important thing. You can see we jumped from Cori to Summit, which is the first intermediate GPU platform, and then finally the Frontier, which is the exaplot platform that we had finally got to. Speed. Turns out that when you've got 9,152 nodes on your computer, you can really take advantage of parallelism. And so what I'm showing you here in the upper right is a scalability curve for a in this case, a 10 hertz simulation of the San Francisco Bay Area and 221 billion grid points. And you can see that as we increase the parallelization, it starts to flatten out because communication starts to take over on the right, but we dramatically increased the speed of these calculations. So in the table on the bottom, today, we can do a 5 hertz, 250 meters per second simulation of the Bay Area on 372 nodes of Frontier in about 1.8 hours. And so that's, I think, pretty impressive. We can do a 10 hertz simulation with a V sub S min of 250 meters per second in 6.3 hours. And we can even do a 15 hertz in about 29.2 hours. So with that background, the point I want to make here, and I think the takeaway message, is we have, through the Exascale Computing Project, substantially changed the state of practice in terms of doing direct physics-based simulations. And I'm showing you 2 examples here. The one on the left is a 10 hertz simulation of the Hayward fault rupture. The one on the right is a 10 hertz simulation of a magnitude 7.5 San Andreas fault rupture. And this really shows clearly the difference between a magnitude 7 and a magnitude 7.5 earthquake in terms of the extent of the zone. But we can do these types of calculations in manageable times now, and I think that's the important takeaway. So this whole notion of a simulated ground motion database really grew organically from the workshops that we had with PEER starting back in 2021. And I'm showing you in every workshop, we poll the participants and get feedback from them. And as we did in this one, there were 261 participants, and we asked them, how can we use this hammer? How can we use these simulations to best impact and move ahead the earthquake engineering community? And so I'm showing you the answers we got in that poll, the top answers on the right. Far and away, the highest answer was make available a database of synthetic motions with open access. Open these to the community. Let the community have access to these motions. Let them kick the tires. Let them use them. Let them evaluate them. And so we've gone, open kimono on this, and we intend to open these to wide access. Second comment was assess the acceptance criteria. And for synthetic motions, we've done a lot on that. I'll mention that. And then the third one was we really want to have an effective and operationally efficient user interface. Everybody has their data set up to grab motions from NGA and so forth. And I think Jack Baker at the first meeting we had said, please don't screw that up. And so we're trying to make the database leverage on PEER's experience with NGA to make it useful to the engineering community. So the activities we're currently engaged in and is development of the regional scale simulated earthquake motions. I wanted to acknowledge that team. Primarily a national lab team consisting of engineering, seismology, and very importantly, computer science. But we also have a couple of PEER institution faculty members that are working closely with us. Dr. Petrona has been really, really important in independently evaluating our motions and helping keep us honest. So that has been a very important contribution. We're now doing some simulations in the LA basin similarly, and ET is leading that along with his student. We've got a great crop of postdocs and PhD students that are working on this, and they've really done tremendous work. And those of you, I hope, that were at the workshop yesterday looked at their posters because they're really doing great work. So the inaugural database, what's going to be in it? We're going to have 50 Hayward fault rupture realizations. The first realization of the database is going to go from 0 to 5 hertz in those simulations. We're using the Gray's-Patarka rupture model to characterize those ruptures, as you heard yesterday. We have 2 types of ruptures. We have the pure stochastic ruptures. We have 25 of those, where Arbin throws the dice and samples the distribution for the slip rate and so forth. And so we've got those that Arbin has built up. And then on the right-hand side, we have got the stochastic rupture scenarios, but with a patch of high energy release that people are using these days based on work coming out of Japan. And so we've got 50 realizations that are going to show up in that database. PEER has been instrumental in helping us define how best we can cast these motions for the earthquake engineering community. And they've developed a really nice user interface that allows you to log in, look at metadata, look at the motions, and selectively download. There's a whole different slew of ways. Those that were there yesterday and saw Holland's presentation, different criteria for selecting motions to download, and also telling you how big those motions are before you push the yes button. We have 15 beta users from cross-cutting academia, industry, and government. And since January, when they came on board, they have downloaded over 5 million time histories and looked at and utilized some of those. So it's so far the database has worked really well. So the database is going to look something like this. The 50 realizations at PEER already on their server. We have over 1 million time series from those 50 realizations, and at 2 kilometer spacing, and that's about 700 gigabytes of data in ASCII format. They like to deliver ASCII format. That is backed up in our simulations by very, very large data sets at Berkeley Lab that we'll use in the future, we think, and I'll mention this and show you how. We have 110 billion time histories that we store at Berkeley Lab on the supercomputer at 6.25 meter spacing, which is the grid spacing in the geophysics model to accommodate a 5 hertz simulation in the Bay Area. So that is held in reserve. It's too big for PEER. For that, you heard yesterday, we've developed some very sophisticated compression and downsampling algorithms to be able to store that data and retrieve that data. There is going to be a lot to look at and analyze in these data sets. I'm just showing you a snippet here of some selected sites in the San Francisco Bay Area. What we've shown here is we have stacked the 50 response spectra from all of those realizations along with the median and plus or minus 1 standard deviation. You go to places like Oakland, you can see clear site response in some of those realizations. So there's going to be a lot of things to explore in this database. So yesterday we took a poll. We had our usual poll, and I wanted to share with you what was voted the most popular future features. Guess what? One of the number one was downloadable response spectra shown for all 50 realizations at every site. And so luckily we've already done that. So we'd be happy to download those graphics so that they're clickable and people can look at that site and see what the frequency, content, and amplitude of the ground motion looks like. Implementation of nonlinear soil representation for near surface layers. All of our initial simulations are essentially linear elastic simulations. So one can use empirical relations to correct for site response. There's been a lot of good work done on that lately, but we would really like, being a physics-based group, to be able to represent those nonlinearities in our model. So we're looking at 2 things. We're looking at developing an equivalent linear representation of the near surface layers, and we're looking at the ability to incorporate fully nonlinear 3D models through the domain reduction method in a near surface volume. So that work is coming. So the other one was, this one surprised me, one of the questions, provide motions in the near surface volume, not just surface, so that we can enable utilization of DRM. That's popular with us. I didn't realize it was going to be so popular with all the attendees, so that bubbled up as an action item as well. That people would like additional ground motion intensity measures in the database for each realization. Ree Nakata of our group has already been working on this. She's been developing for each realization spectral amplitudes and pictures of spectral amplitudes that one can look at. And so that'll be something addition that we can add and upload to the database. Then finally, there was a desire to create an online chat tool of some sort for application examples and discussion of best practices. And so we will try to work on that as well. So I'll just leave you with one thought that I think is important. This is the initial realization of the database, our first shot at this. We really desire and want feedback from the community because we view this as a living database that will continue to evolve and add features. And so we are working with Pedro Arduino and Frank from SimCenter, and we are delivering DRM boundary motions to them from our 3-dimensional model database, and they're kicking the tires and figuring out how to utilize these things so that they can do a local soil structure interaction analysis, including nonlinear material behavior and so forth. So we're already looking forward and thinking about leveraging bigger and different applications based on the technical pull. And I am out of time, so I'm going to stop there.